Alright, hello everybody. Let's continue our lecture. We are almost at the end of the course really. And before we wind up this course, I thought it's good to have a kind of some sort of a summary of all that we discussed, because we have talked many things in this course. And before we wind up, it's actually good to see everything in some sort of a together sense. Actually, kind of an overview you should have. And even if you do not remember all the details, I think at least this much you should remember at the end of the course actually. So, let us get started quickly, and if you remember the topics that we covered in this course, we started with a small introduction and motivation, then quickly went through this review of state space approach, and then followed by review of matrix theory as well. Then we also had a review of numerical methods, and followed by static optimization. Then we went on to calculus of variations, and then started optimal control actually. So, essentially those of you who did not have too much of background, I thought it is still possible to kind of catch up with, then that is these reviews will actually help you there. And these two lectures I will actually directly start with static optimization, because the course is on optimal control. So, all the other things there is no time to review again. I think we will directly start with a little bit concept of static optimization. Then optimal control, we derived these necessary conditions of optimality, and we can quickly see that actually it leads to this 2-point boundary value formulation. We also had a generic transversality condition, and then talked various things about that actually. And we went on to solve these classical techniques to solve this numerical problem, 2-point boundary value problem. Essentially, we talked shooting method, gradient method, and quasi-linearization method. That was followed by this this very standard LQR theory, which we devoted a few lectures to study this in fair detail. We studied Riccati equation solution, stability and robustness properties, extensions of LQR in various ways, and then straight transition matrix approach solution, and followed by its application in missile guidance and all that actually. Then we went on to discrete time optimal control. First we had generic formulation, then discrete LQR as well. On the way we had this overview of flight dynamics, and then also talked about optimal missile guidance through LQR. And then this we went on to nonlinear formulations and started with this extensions of LQR idea in the SDRE framework, followed by theta D design. Then we went on to dynamic programming approach, which was HJV theory, then approximate dynamic programming, followed by adaptive critic design. Then transcription method, pseudospectral transcription especially, we had a class actually. That was followed by this model predictive static programming, and we also had this various guidance applications of this technique. And then we extended that to this spread control idea with the control parameterizations and all. And then we also had a glimpse of very recent development which talks about generic MPSP actually. And then we also discussed LQ observer, and then had an overview of state estimation. That was followed by detailed kind of discussion about review of probability theory, random variables also. And then we went on to derive the Kalman filter using various frameworks. First in continuous time framework CKF, then discrete time framework DKF, then continuous discrete Kalman filter, where system dynamics was continuous but measurement was discrete. And then we extended these ideas to something called extended Kalman filter, which is heavily used, and then again we discussed both in continuous time as well as continuous discrete framework. And before we wind up, we also discussed something called uncentered Kalman filter, and then had a glimpse of how to implement it really actually. Then we also discussed integrated estimation guidance and control, followed by the so called linear quadratic Gaussian design, where you design the control from LQR, whereas states come from Kalman filter. And then we also talked a little bit on neighboring optimal control, sufficiency conditions of optimality, and then we have about 3 lectures on constrained optimal control, where we discuss about control constraint problems as well as state constraint problems. Okay. And before we wind up, we also had 2 lectures on optimal control applications to distributed parameter system. So, overall if you see the course topics are very wide, okay, and starting from introduction, reviews of various material to basics to classical topics to numerical solutions to advanced topics to various applications in flight control, all that actually. So, I thought towards the end I will just go one by one slowly and then try to kind of summarize what all we have discussed. But also on the way I will not go too much into aerospace applications, especially this flight dynamics, guidance and all that actually. I will confine myself to review of only the tricks and techniques basically. I will not follow any examples, I will also not follow any applications per se basically. Alright, so let us get started. This is how we started the course on 2 lectures on static optimization. And first we discussed something like a scalar cost function of vector variables. Okay. So, we want to minimize this j of x is a vector, but j is a scalar. And to have this condition met, what we observe is that j of x star plus delta x minus j of x star has to be always greater than 0 irrespective of the sign of delta x or direction of delta x really. Okay. It does not matter which direction you go, but still this relationship if it satisfies, then x star is a minimum point actually. Okay. And for that we put the Taylor series expansion for that, and then first term cancels out, the remaining term was sign sensitive, we want to make it insensitive, things like that. So, that led to the necessary condition that first gradient should be 0, and followed by sufficiency condition that the Hessian matrix evaluated at x star should be positive definite also. Okay. And also observe that further conditions like third derivative, fourth derivative, all sort of things are possible, but they are also difficult to use in practice as I mean unless the problem is a scalar problem really. Okay. So, we did not bother so much on those aspects actually. Then we went for this constraint optimization problem, and we started with this equality constraint. Okay. So, the cost function was scalar, the x was still a vector, and this set of constraints, equality constraints, was actually m constraints, m dimensional variable actually. Okay. So, the solution procedure turns out to be like that, j bar okay, is j of x plus lambda transpose times f of x actually, because that is how it is. And then this comes from this Lagrange existence theorem sort of thing, which tells that okay, there exists a set of Lagrange variables lambda, again same dimension as f, and if you construct a augmented cost function like this, okay, and then it is equivalent to kind of see this problem in n plus m dimension, the dimension becomes more, but essentially j bar becomes a free optimization problem in the variables x and lambda together. So, then we can go back and apply this necessary condition in that setting, and then come up with this idea that okay, del j bar by del x has to be 0 and del j bar by del lambda should also become 0 simultaneously. So, this leads to this n plus m equations with n plus m variables also. So, it is possible to solve together. After we solve, we discard lambda and take x star, whatever x star comes from there actually. Okay. Then we had a sufficiency condition kind of check if you want to do. Now, we have to formulate this kind of a matrix, then take determinant, make it equal to 0, and then solve for roots. And if this equation has only positive roots, then it leads to a minimum, and if it has only negative roots, it leads to a maximum problem actually. Alright. So, next we followed up with this inequality constraint sort of thing. So, we had this same problem, the cost function is still a scalar, but it is now subjected to m inequality conditions actually. Okay. In general, it can be less than equal to 0, but even if it is positive, then you can flip the sign and put everything like less than equal to 0 basically. So, then the idea was to introduce a set of slack variables mu1 to mu_m and convert these inequality constraints to set of equality constraints actually. However, this because it is inequality constraints, we do not know how far they are from 0. So, we really do not know the numbers for this actually, mu1, mu2 up to mu_m, we really do not know the numbers. We just know that there exist real numbers like that, for which this inequality constraints can be converted to equality constraint. But then there was a necessity of finding out conditions and all. So, then we augmented that the j bar becomes not only a function of x and lambda, it now becomes a function of x, lambda and mu also. So, then the necessary conditions expands to that del j bar by del xi, del j bar by del lambda j, and then del j bar by del mu j also basically. Okay. So, the dimensionality of the problem becomes n plus 2m now basically. So, we went ahead and then tried to analyze all these conditions, and ultimately it turns out that lambda j gj is equal to 0. That means either lambda j has to be 0 or gj has to be 0. And then we went back and then tried to analyze all these conditions, and then essentially it gives us this so called KKT condition, that is Karus-Kuhn-Tucker condition, which tells us that these necessary conditions are something like this. This equation has to be satisfied, this is also satisfied. However, you have now you have to analyze the various possibilities, and for j of x has to be minimum, then these conditions have to be satisfied actually. Okay. Similarly, for j of x it has to be maximum, these conditions have to be satisfied. Okay, that means these have to be opposite sign and this has to be same sign actually, g and lambda basically that way. And we also had examples on the way to demonstrate how it is possible to apply analytically and all that. So, if you are curious or I hope you have gone through that lecture already, but in case you have not gone through, then you can see that lecture also. So, this is what it is. One should explore all possibilities in KKT conditions to arrive at an appropriate conditions. Then also remember that KKT conditions are only necessary conditions, and sufficiency check demands the concept of convexity as well. And we summarize the results that if j of x is strictly convex, strictly concave, whereas Gj happens to be convex, then it leads to a maximum case. Otherwise, if it is strictly convex, both are and this is convex, then it leads to a minimum case actually. Alright, so that kind of a thing. Then we proceeded further that we observe that all this type of analysis is too much to do for practical problem. If the problem becomes more and more difficult, these conditions analytically applying them becomes quite difficult actually. So, there was a necessity of kind of go through little bit of numerical solution approach as well. So, we studied couple of techniques as well. Okay, the first one, the philosophy remains same. So, the philosophy is something like this: you start with a meaningful initial guess and then find a search direction, from some direction has to be found out, then update the guess value properly in that particular direction for some step and repeat the procedure until there is convergence. That means, you do not see any further improvement in this sense actually. So, that is the generic procedure for all numerical optimization. And then we saw that okay, the very first thing that comes to mind is steepest descent search, and steepest, this is very intuitive as well. All that you do is j of x k plus 1 is you expand about j of x k in Taylor series. So, then neglect the higher order terms, keep only the first order expansion up to gradient value, this term, then it turns out that this j of x k plus 1 minus j of x k, this term is approximately equal to that actually. So, if you consider that as alpha times pk, then pk, if you really want to kind of have a decrease in the value of j of x k plus 1 compared to j of x k, then this quantity has to be always negative, negative into some quadratic term sort of thing. So, it makes sense to kind of do pk nothing but negative gradient basically. Okay. So, then it is guaranteed to have some sort of a quadratic term like this. So, it is guaranteed to be less than 0 basically. So, it will keep on decreasing basically. But this property happens to be very local. So, there was necessity of fine tuning more, and then there are concepts like line search, and then there are concepts like conjugate gradient methods and things like that actually. So, the another method was something like Newton's method, and Newton method a little bit kind of takes help of an analysis result, which tells us that that on the optimum value, the gradient of that delta grad j has to be 0. So, if you assume that okay, x k was not optimum, but x k plus 1 needs to be optimum, then gradient at that point actually x k plus 1 needs to be 0. So, now observing that, suppose we want to expand this vector valued function now in Taylor series, then it turns out to be something like that. Now, it gives us a platform to keep some sort of like a quadratic term basically. So, we proceed on almost the similar sense, but instead of this pk becoming a function of gradient only, like here, okay, here it was negative gradient, but here it turns out to be some sort of a gradient function, but negative gradient, but this also helps actually, this Hessian matrix inverse and all that actually. So, advantage wise it leads to fast convergence, but drawback is this Hessian matrix inverse is not trivial to compute in general, and it may need little bit more computation actually. Okay, so, with that background we proceeded to calculus of variations, and then calculus of variations, first we had some concepts like that, what do you mean by function in general function space, and what do you mean by functional in calculus of variation actually. Essentially, it is kind of a function of function, but that j of x of t, where t is the independent variable, whereas x is a dependent variable of t, and j is a function of x of t basically. So, that kind of things are called functional, but here if you simply take x of t, where t is independent variable, then it is a function essentially. So, we studied various concepts and things like that about that, and we finally land up with an observation that if you really want to claim that some functional is optimum, then what is the condition necessary basically. Okay. So, it turns out that if I define gradient of j, something like j of x minus j of x star, which is greater than equal to 0, okay, it has to be greater than equal to 0, then j of x star is essentially a relative minimum actually. Okay. If gradient of j happens to be always negative, okay, then j of x star is actually relative maximum. Okay. So, what does it mean? Now, you remember that x is not just a value, but it itself is a function actually. Okay. And then what you are looking for, that increment of j has to have same sign as long as x of t lies in the neighborhood of x star of t essentially. Okay. And if that neighborhood condition is relaxed, that means epsilon can be very high in like that. So, arbitrarily large epsilon, then you tell, okay, j of x star is nothing but a global optimum value basically. So, pictorially it turns out to be something like this. If we tell that the dotted line is actually optimum path, okay, then around that we can draw any other curve, okay, and the difference between them is nothing but the variation actually. Okay. So, what you are telling here, that j of x means if j of x evaluated on the solid line path and j of x star is evaluated on the dotted line path actually. Okay. And irrespective of whatever variation we want to take around the optimum value, if this condition is always satisfied, then j of x star is actually a relative minimum. Otherwise, if this condition is satisfied, it is a relative or local maximum actually. Okay. Then we thought, there was a necessity of deriving necessary and sufficiency conditions for optimality, and then we observe that very close to static optimization in calculus of variations also, turns out that the first gradient or this first variation has to be equal to 0 for all admissible variations of x actually, and sufficiency condition tells that second variation has to be positive for minimum or second variation has to be negative for maximum actually. Okay. Then there was a fundamental lemma based on which we derive lot of necessary conditions and all that actually, and that tells us that for if for every continuous function g of t, this is valid, this integral is valid, okay, where this variation is continuous in this time interval t naught to tf, then g of t has to be identically 0 throughout the interval, and we actually gave a small proof for that as well actually. Okay. Alright, so based on that observation, we formulated some sort of a variational optimization problem now, which tells us something like this. We are interested to optimize this functional by appropriate selection of this x of t. Okay. And t0 tf we started with fixed value and things like that. So, all that it was necessary is somehow find out conditions for first variation equal to 0 basically. So, we went ahead and analyzed that expression and then took the first variation and things like that and excited this theorem, okay, that if for every continuous function g of t this integral is 0, then there is no other way, g of t has to be 0 actually. So, using this fundamental lemma, it turns out that we can derive something called Euler-Lagrange equation, which turns out to be something like that, del L by del x minus d by dt times del L by del x dot equal to 0 basically. Then there is a associated transversality or boundary condition as well, which turns out to be something like this actually. So, the derivation is there in the as part of the lecture. You can revisit the lecture and then find out it also basically. Okay. Then we also observe on the way that there is a generic transversality condition, which turns out to be something like this, and then using this transversality condition in various cases, your boundary conditions can be derived. And suppose it has fixed endpoints, that means t naught, x naught and t of x both are fixed, then it does not give any additional information. However, if t naught and t f are fixed, but x naught and x f are free, then you have to use this condition. And again, depending on whatever constraints we have, we have to neglect that whatever is free, the coefficient has to be 0 actually. Okay, so there we will get another boundary condition actually that way. All right. So, this is then we extended this concept to multiple dimension problems, where x of t is actually a vector value now, it has n components actually, and the idea was again to make sure that first variation is 0 for arbitrary delta x, and then it turns out that the necessary condition turns out that del L by del x minus d by dt of del L by del x dot 0, but remember these are now vector equations actually, okay, component by component you can write n equations actually. Okay. Now, similarly, transversality condition also turns out to be fairly same, assuming T naught and Tf are fixed actually. So, that this term doesn't come actually. Okay. Tf and T0 are fixed, then this variation of Tf is 0 and variation of T naught is also 0. So, this entire term drops out actually that way. Alright, now we are not interested in only free optimization. So, we slowly want to introduce state constraints and things like that. So, we also studied this constraint optimization problem, where a algebraic constraint comes along with the cost functional also. Okay, so, then we told the similar Lagrange existence theorem also holds good, which actually tells that we can construct J bar something like this, where lambda comes inside the integral. That means, lambda is actually no more a constant value, but it is a time varying variable actually. Okay. And then you can actually go ahead and apply the EL equations and things like that, and then come up with this sort of conditions actually. Okay. So, this tells us that state equation is valid, and then associated with that the lambda equation is also valid. Okay. And that we will see little later also actually. I mean, we have seen how do we kind of use that lambda dot equation and all that actually that way. Okay. Then transversality condition in vector dimension is also similar. Okay. And then you can use this EL condition along with the transversality conditions to arrive at some optimal control or optimal trajectory essentially basically. But the problem dimension is now something like this. So, x is n dimensional, lambda is n tilde dimensional, and Tf, if it is free, happens to be one more dimension actually. Okay. Alright, so it is actually n plus n tilde plus 1 dimensional problem that we are talking about actually. Then that was the kind of calculus of variation summary sort of thing, and more details obviously are there in the detailed lecture detailed lectures. But then after that we wanted to kind of use those concepts in optimal control problems actually. So, the objective was something like this, to find an admissible time history of the control variable u of t. T varies from T naught to Tf, which causes the system governed by this nonlinear system dynamics to follow an admissible trajectory, and on the way it should also optimize a meaningful performance index of this form, which is typically called the kind of Bolza problems, where it is fairly generic. We consider, can account for many systems actually, many practical problems, and also should force the system to satisfy appropriate boundary conditions as well. Okay. So, these are the objectives we started with, and then we also observe what are meaningful boundary conditions per se. Can have fixed endpoint problems where both the things are fixed, or you can have free endpoint problems, either both are completely free, or the most of the time it also turns out that the final condition is free, but it is kind of constrained to lie on a curve actually, especially let us say orbit transfer problems of satellite and all that. It does not matter where you join, but as soon as you join the orbit and then have the orbital condition, then that is the orbit that you are going to follow from there onwards actually. Okay. So, that kind of things require that free endpoint problems of formulation, where it is not completely free, but the final point is required to lie on a curve actually. Okay. And we went ahead and formally started the problem, performance index is something like this form, and we had a path constraint in the form of system dynamics now, okay, in state space form, and we had some boundary conditions where initial state conditions are given and Tf is fixed and x of Tf is free sort of thing. So, then we formulated an augmented cost function, then took defined the Hamiltonian L plus lambda transpose F, only that part of it, and then analyze the first variation, which has to be equal to 0 basically. The first variation turns out of this form, okay, and then exciting the fundamental lemma of the calculus of variation, all the coefficients needs to be 0, which gave us a bunch of conditions, which tells us that something like state equation, co-state equation, optimal control equation, and boundary conditions. So, state equation is x dot is f of t x u, lambda dot is minus del h by del x, all sort of things actually. Optimal control equation is del h by del u, and boundary conditions are this form. So far so good, but also observe that these two equations are together, that means state equation develops forward, and co-state equation, and actually there is a final boundary condition here, so the co-state equation develops backward actually. And then these led to so many observations like this. The state and co-state equations are dynamic equations, and unfortunately it turns out that if one is stable, the other is unstable actually. Okay. Whereas optimal control equation is a stationary equation, it means just an algebraic set of equations actually. And the more difficult thing or the critical observation is the boundary conditions are split actually. Now, even though it is a 2n dimensional problem, The boundary conditions partly it is given at initial time and partly it is given at the final time. Okay, that is the whole problem essentially. So, this essentially known as curse of complexity, okay, and then it also is known as 2-point boundary value problem, which demands some sort of computationally intensive iterative numerical procedures, and it leads to this open loop control structure as well actually. So, that is the type of analysis it leads to the difficulty of problem and all that actually. Nevertheless, there are classical numerical methods, people have attempted it, and we have actually discussed 3 methods as part of the lecture, and quickly I will review 2 methods essentially here. So, one we talked is suiting method, and suiting method philosophy is we initially we observe that this equation, the set of equation, the difficulty is the boundary conditions are not available at the same time. So, because the state initial condition is available, so I will guess a initial condition for co-state also, so that these 2 equations can be propagated together forward actually. So, that is what is done here. Initially, you come up with some sort of a guess value for lambda 0, and then x 0 lambda 0 taken together, you can integrate the equations forward. On the way, you keep solving for optimal control as well, and then keep marching ahead, and then finally land up with some value of lambda f, which is not the desired value. So, obviously, there is an error, and utilizing that error, we have to kind of update this lambda 0 value. So, this is the initial case, this is the after first iteration, things like that. So, we update it and then repeat the procedure and end up a little somewhere else actually, which is hopefully little more better than what we initially guessed actually. So, then we keep on repeating the procedure until you get the solution actually. The problems in this method is the high sensitivity with respect to the initial value of co-state. Remember, for stabilizing control, for stable plant, the co-state equation is actually unstable. Okay, so, if you have a little bit inaccuracy in the initial condition value, then it actually leads to a lot of inaccuracy in the final value, and eventually the entire procedure may break down, it may not even converge actually. Okay. And this effort of guessing this co-state value is even more difficult, because co-states do not have any physical meaning. They are nothing like distance, velocity and things, current, voltage like that, they are nothing like that. So, we do not know what kind of numbers we need to choose actually. Okay. So, that is why it is usually done through guessing some sort of a control history. So, we guess a control history from T0 to Tf, we have x 0. So, we go there with that control history, find out lambda f from the boundary condition, and integrate the co-state equation backwards to come up with some sort of a lambda 0 value. Okay. And so, this is the critical drawback of this method. The co-state equation is typically integrated in the forward direction, and hence you are actually integrating an unstable equation in the forward direction, which is not good, and hence long duration prediction is not good actually. So, that is why people have thought about divide and rule policy, something called multiple suiting and all that actually. So, divide the path, break up the path into 2 parts, 3 parts and things like that, finite number of segments really, and then you can actually integrate these problems in segment wise sense. But also remember, while doing that, the continuity and smoothness at the joining points have also be ensured. That means, we have to introduce more and more constraints to kind of ensure that actually. Okay. So, this approach is called multiple suiting, and a generalization of that is something like direct transcription, and we also had a glimpse of what is called direct transcription method as part of this course actually. Now, coming back to gradient method, which is another idea actually. What we tell is, okay, we start with a guess history of the control value from T0 to Tf, and with respect to that guess history, okay, we assume that if you use that guess history in the state equation, then whatever trajectory we get, we assume that is kind of close to optimal in the following sense. That the state equation is satisfied, co-state is also satisfied, the boundary condition is also satisfied, whereas the co-state equation is the optimal control equation is not satisfied. And remember, out of all these things, whatever conditions we have, everything needs to be satisfied, only you can talk about a kind of solution being optimal, otherwise not optimal actually. So, here you are assuming that, okay, the optimal control equation is actually kind of getting not satisfied, everything else is getting satisfied. Then the idea is, how do you iterate on the control history, so that equation will also get satisfied without hurting all these conditions actually. So, then we analyze, okay, if you talk about first variation of j bar, this turns out to be something like this, and we are assuming that we are assuming that this equation satisfied, boundary condition satisfied. So, this is 0, co-state equation satisfied, this is also 0, and this state equation satisfies, this is also 0. So, we will end up with only this term actually. So, that is why del j bar turns out to be like this, and hence if you really want to make it kind of negative decreasing value and all that, then you take del u is nothing but minus tau times del s by del u. So, this term becomes some sort of a quadratic term like this actually. So, this is guaranteed to decrease actually. So, that is the whole idea of gradient method, which is also inspired from this steepest descent method in static optimization actually. Alright, so then idea is, okay, we select this del ui something like this at all over from T0 to Tf, and then this lead to this kind of update actually from I to I plus 1 actually. Okay, right. And eventually if it keeps on decreasing, then eventually this del j bar is going to be 0, and when del j bar is going to be 0, the only when it can happen is del s by del u equal to 0, because all these are quadratic terms, and integration of quadratic terms means unless this value itself is 0, this cannot be 0 actually. So, by ensuring that this is 0, we are also ensuring that del s by del u is 0, and that is nothing but the optimal control equation actually. So, that leads to this gradient method idea basically there. So, this is what is summarized here. We assume a control history, which is again assuming a control history is typically not trivial. We have to really look at the problem, and then according to the problem, you have to select it judiciously actually. Okay. Then we first, using that control history, integrate the state equation forward. Then at the end, you evaluate the boundary conditions for lambda, and then using that boundary condition, you can integrate the co-state equation backward and update the control solution. This can be done both two ways actually. It can be done either be done at each step while integrating co-state equation backward, or after integrating the entire co-state equation from Tf to T0, and then you can update the control history, all the control history from T0 to Tf at one go basically. Alright, so this procedure needs to be repeated until convergence, and that is what the gradient method is actually. On the way we have given some examples also, including some sort of a Michel turning example and all that, which is a little more realistic problem actually. Alright, then there was a quasi-linearization method also in that particular lecture. So, if you are interested, you can go back and study that as well. Then we migrated to this linear quadratic regulator theory, which is there in which was developed around 1940s and 50s, and it is one of the branch of optimal control theory, which is heavily used in practice also. So, and this essentially leads to the state feedback form of control design, even though the system dynamics has to be linear and all that actually. So, that is what it gains significance in that point of view. So, the performance index was selected to be quadratic. There was a penalty, terminal penalty, and there was a path penalty, all of which are quadratic. Path constraints needs to be linear, and boundary conditions are something like this actually. Okay. So, essentially once you analyze these necessary conditions, and we observe that phi of xf is this one, then L of xu is this one. So, Hamiltonian is L plus lambda transpose f. So, L part is this, and lambda transpose f is nothing but this part actually. Okay, x dot is f of xu, so x plus bu. So, that is what Hamiltonian is, and then using these necessary conditions, it turns out the state equation is nothing but x dot is x plus bu, co-state equation is minus of qx plus transpose lambda, optimal control is del s by del e equal to 0, which essentially leads to u is nothing but minus r inverse b transpose lambda, and boundary condition is s lambda f is sf xf. Now, these are the conditions, but how do you use it actually? So, observing the fact that at t equal to Tf, lambda is a linear function of xf, we thought, okay, why not we guess something, okay, lambda of t is p of t into x of t, but he also gave solid good mathematical reasons why it needs to be in that form only basically. So, there was some uniqueness theorem also. One idea is there that if there is a solution, then that has to be only solution for LQR problem. And also there are other ideas like vector space methods. If you see Leuenberger book and all that, it has to be lambda of t, each component of lambda of t has to be kind of linear functional of all these things actually, okay, of x. So, this is it has to be written in this form only. But once we write it, then we can analyze lambda dot, and then you can use x dot is x plus u state equation, u is r inverse minus r inverse b transpose lambda, optimal control equation, and then lambda is nothing but p times x coming from here, whereas lambda dot is this equation coming from co-state equation. So, once you put everything and then take everything together to one side, turns out to be like that. So, x is arbitrary, it cannot be 0. So, then the coefficient has to be 0. That leads to this famous Ricardi equation with boundary condition that p of xf, this boundary condition is there, from which lambda f is nothing but p f x f from this relationship. So, p f x f is nothing but s f x f. So, p f has to be s f actually, okay, this condition. So, you think that okay, at t equal to t f we have boundary condition for p irrespective of whatever is the initial condition of x, it does not matter actually. So, invariably no matter where the initial condition of state be, we can actually start with this boundary condition of Riccati matrix P, okay, and then use this Riccati matrix equation, differential equation to integrate it backwards from T f to T naught, then store that values and then use it online as lambda equal to P times x, and then this control, okay, is nothing but minus R inverse B transpose lambda, and lambda is P times x actually. So, that gives us some sort of a R inverse B transpose lambda B transpose times P is nothing but the gain matrix K basically, okay. So, this is what is written here, U is nothing but minus R inverse B transpose P, this is a gain, and then essentially this leads to this U equal to minus K x form, which is in state feedback form. But also we observe on the way that if T f goes to infinity, okay, and Q and R are constant matrices, then P dot is identically 0 for all time. So, exciting that it turns out that this is 0. So, that means it results in the algebraic Riccati equation actually, which is very commonly used all over actually that way, okay. So, you do not have to really solve for some differential equation and store the matrices offline and all that actually on board and use it online and all that. Essentially, you can just solve one equation, okay, and if it happens to be a difficult equation, you can solve it offline still. And then keep one matrix in memory and then start using this and then tell okay this gain can be computed like that, and I have the gain there, I mean the gain matrix is available. So, the control happens to be a state feedback form, and that too a linear state feedback form actually, okay. Then we also kind of analyze the stability of the closed loop behavior. So, we notice that the closed loop can be written something like this, and selected a Lyapunov function something p x transpose p x, and p happens to be, see remember this is a nonlinear equation, it can have multiple solutions also, but we are interested in that particular solution which is positive definite actually. So, once you take that equation and put it here, then this becomes a positive definite function, and all that it was necessary is to show that v dot x is negative definite, and we are able to show that actually, okay. So, then it tells us that the closed loop system is essentially asymptotically stable, and because it is also radially unbounded and all that, it turns out that it is a globally asymptotically stable. I mean if you see the solution nature, we really see that for constant A and B and constant K, its solution nature will tell that it is actually globally exponentially stable also basically, okay. Alright, now to find out the optimal cost, we had some analysis of this cost function, especially when t goes to infinity, and it turns out that the same thing can be written as something like this, negative of E dot here. So, it can be evaluated, the derivative and integral will go, it can be evaluated like that, but V of infinity is nothing but x of infinity coming here. So, x of infinity is 0, that part goes and you will end up with only x naught actually. The moment we know x naught, we can actually say what the optimal cost value can be actually. Yeah. Then we extended this LQR design to several concepts and ideas and all that. First we did some cross product term, and then told how to actually reformulate the problem so that cross product terms can be also solved. Then we also went to this rate of state constraint or weightage on rate of state formulation, and essentially leads to this cross product term formulation again. So, it was possible to solve. We also saw weightage on rate of control, if it is there what to do, it essentially led to this PI sort of control essentially, okay. And then we had this LQR design with prescribed degree of stability also. So, that is how it is. And then LQR design for command tracking, okay. So, this prescribed degree of stability tells that okay in the closed loop the eigenvalue should lie left of certain vertical line, okay, which is alpha away from the imaginary axis basically. So, it is possible to do by formulating the cost function in such a way that x transpose q x plus u transpose r u, that term you multiply that with e to the power 2 alpha t, okay, and then reformulate the problem, and it is possible to show that all the eigenvalues of the closed loop system will be remaining left side of a vertical line which is alpha away from the imaginary axis actually. So, that is the prescribed degree of stability. Then we also saw how to extend that for command tracking problems, okay, and also saw how to extend that for inhomogeneous systems. That means x dot is x plus v u plus c, if you have something like that, what to do about that. And also a slightly different formulation which talks about robust control through LQR design, especially for parametric inaccuracies, and also again lands up with this integral control feedback sort of ideas actually. Okay. Alright, so after that we again went ahead and extended that for state transition matrix approach. I mean we relooked the problem and tried to kind of solve it using the state transition matrix approach ideas, where we write this x of t as something like state transition matrix times xf now. Okay, and lambda of t is also this state transition matrix for lambda times xf, and at t equal to tf this condition has to be satisfied. So we got the boundary conditions at tf actually. Then it turns out that the x dot and lambda dot can be written something like this, and hence substituting these expressions we can write like that. So these state transition matrices will satisfy this kind of equation essentially. So we have these equations and we have these boundary conditions essentially. So we can solve that actually. Okay. And also notice that x of t naught can be extracted from xf that way. Okay. And substitute back here. So x of t and lambda of t becomes like this, and then finally u of t can take this form. Okay. And this can be again written as something like k of t times x naught actually. Okay. Now you can tell, okay, my t naught is t, then it will essentially lead up with this u of t essentially. So that is sample data feedback law sort of thing actually. So u of t essentially can be computed again as minus k of t times x of t really. Okay. Then this was, we extended that to hard constraint problem also and told, okay, here the xf was free, but here xf is a hard constraint sort of thing. That means xi of tf has to be equal to 0 for I 1 to q. Okay. So for a set of states, okay, part of the states should be identically equal to 0. That's a hard constraint actually. So then we have to formulate this new also basically. I mean this part will come as additional part of it. Okay, and then we analyze this in a fairly similar way. So again we will end up with the state transition matrices being something like this, and boundary conditions now are different. Okay, the boundary conditions turns out to be something like this actually. Okay, that means as long as t is away from tf, things are okay, but when t approaches towards tf, remember this matrix is actually a singular matrix actually. And because of that, there was a, I mean, if you see this control expression, there is a inverse of that, and singular matrix inverse is obviously infinity and all that actually. So we have a problem in this. There is a singularity of the control actually. So after some time, the control is guaranteed to go to saturation. And that there you time, okay, you can apply the saturated value or something, but then not a very good formulation actually. Okay. So we saw all that actually that time. Okay. Then we also had a little bit glimpse of frequency domain interpretation of LQR. So we thought optimal trajectory is dictated by this closed loop system dynamics, and then we assume that AB is stabilizable, whereas at A square root of Q is observable, and then we define this open loop characteristic polynomial as something like this. And then we analyze the closed loop characteristic polynomial, and it turns out to be given in this form actually. Okay, so this particular thing I plus k times Si minus A inverse times B, this part is called return difference matrix, and then this loop gain matrix is something like this actually. Okay. The algebraic Riccati equation, if you start from there, okay, so it is then you can add and subtract this SP term, do lot of this algebra, and then define this polynomial phi of S Si minus A inverse, and then carried out to this pre-multiply and post-multiply operation and all that. Essentially, it will ended up with some equation like this, which is called Kalman equation in frequency domain actually. Okay, it's possible to use this equation to derive the gain matrix values actually. I have given examples as well. And it turns out that using this analysis further, and it turns out that the gain margin is minimum half, and maximum can be as high as infinity, and the phase margin is always greater than equal to 60 degree in LQR design, which is very good. But also remember, these margins are valid only with exact state feedback. The moment you put something like a observed state or estimated state feedback, then these are no more valid actually. Okay. Okay, before we wind up the LQR topic, we also discussed something like discrete time LQR and discrete time optimal control theory in general first before going there. So the performance index was all given in discrete time, and path constraint were also given in discrete time. Augmented cost function is also like this, something like that. And then we had Hamiltonian described as a very standard way. The only difference here, of course, is the association of lambda k plus 1 here is not lambda t. We assume that if you see the continuous time, we expect that here should be lambda k, but here it turns out that it starts with lambda k plus 1 and not lambda k basically. So, we had this Hamiltonian formulation that way, and then again this j bar formulated that way, and we have to we have examined the increment of j bar due to increments in the variables of x k, lambda k and u k also. And then ultimately we will end up with this state, co-state, optimal control and boundary condition equations as well, very similar to what we know before. The only difference is this instead of wherever lambda k was there, or wherever we expect that lambda k will be there in the right hand side, turns out to be lambda k plus 1 actually. So, to know the u k, we actually need to know lambda k plus 1 actually that way. Okay. And otherwise it is fairly similar. This state equation develops forward, co-state equation develops backward. Remember, lambda k is a function of lambda k plus 1 like that, and optimal control equation, stationary equation needs to be solved to get the control value u k actually. The boundary conditions were also given like that. So, now coming to discrete LQR, so we have a linear form of system dynamics and discrete settings. There is no particular advantage of taking whether the time invariant or time varying. So, we consider time varying in general. And then performance index is quadratic as well. Okay. The Hamiltonian and all we can define, and then it ends up, we will end up with state equation, co-state equation, optimal control, boundary condition, all that actually in the discrete framework. So, again the state equation same, co-state equation like this, but lambda k happens to be a function of lambda k plus 1 now, and u k is also a function of lambda k plus 1. Okay. So, with that observation we can try to apply this and then try to derive this equivalent Riccati equation and all that. So, here again we assume lambda k is nothing but p k times x k, and that went ahead and derived this Riccati equation, which is again a backward recursion actually. Okay. Then optimal control equation can also be analyzed, and it turns out that it can be given in this form, where the entire big matrix what you see here is nothing but the Kalman gain k k actually. So, u k is minus k k times x k. Okay. So, this is the DLQR design part, but it essentially turns out that there is not much of guarantee assurance sort of thing here. So, there are possibilities actually. Okay. So, the possibilities like when you start with p n and try to integrate backwards actually, it can actually converge to p infinity 0 or p infinity some finite value which is greater than 0. It converges to some p infinity strictly greater than 0, or there is no convergence at all actually. Okay. So, depending on the situation you have to analyze or take that particular value which is conducive to us actually. Okay. So, essentially if you tell that okay, under steady state I have a constant matrix, that means p k equal to p k plus 1 equal to p. So, in that case the algebraic Riccati equation becomes this way. Okay. And this algebraic Riccati equation can have non-positive, semi-definite, non-symmetric and even complex solutions actually. So, if the limiting solution of ARE exists, okay, and is not guaranteed to exist by the way, but if it exists, then k happens to be like this actually, which is actually nothing but a constant gain. In that case, we can write u k as minus k times x k, where k happens to be a constant gain actually. Alright, so those are discrete time, but again because of the advancement of computer technology and all that, now people do not talk discrete time, do not give that much importance to discrete time formulations actually. So, continuous time results can be implemented with very high frequency update, then it is as good as applying that with discrete time theories are becoming more or less kind of obsolete actually. So, that too much importance was not necessary actually in that sense. But anyway, coming back to the further extension, we discussed about something called state dependent Riccati equation design, which is nothing but XDRE design sort of thing. And this is actually a slight extension of the LQR idea for a particular class of nonlinear problems, and where the performance index is still given as quadratic looking form. It may not be really quadratic. Remember, q is a function of x now and r is a function of x also, but as long as it is written like that, it feels as if it is quadratic actually. Okay. And system dynamics happens to be in this form, which is control affine, that means linear in the control variable, but whereas it can be nonlinear in the state variable actually. And then the conditions necessary were something like this: f of x, b of x, q of x, r of x has to be at least class ek, k is at least 1. So, these are all smooth functions. The first gradient vector at least is continuous actually. And f of 0 has to be 0, that is a critical observation in this form. Then v of x has to be non-negative all the time, okay, in the domain of interest. J has to be globally convex. Remember, q and r are not really positive semi-definite or positive definite matrices. So, we cannot guarantee that. Okay. So, but condition is irrespective of whatever they are, they have to be, the entire function has to be globally convex actually. Okay. And then one critical observation is whatever this f of x, it has to be written in this form, which is like linear looking form sort of thing. It is not really linearization, remember that. The Taylor series linearization is not valid. We simply write it as some looking form actually. In other words, if it is x minus x cube, you can always write as 1 minus x square whole multiplied by x actually, that kind of thing. So, we write it that way and assume that a of x, b of x is pointwise stabilizable at all points actually. Then what happens, the cost function appears to be linear, I mean quadratic, it feels like quadratic. If you close your eye for qx and rx for a second, then it feels quadratic. And the system dynamics is written in this so called state dependent coefficient form. That means this f of x is written in a of x times x. So, now it also appears to be linear, okay, not really linear, but appears to be linear. So, now linear looking state equation and quadratic looking cost function. So, the idea here is, okay, we can treat for a moment that at any particular grid point it is actually a quadratic regulator problem, and hence we go back to the LQR theory and tell, okay, this we solve this required equation at every grid point online, and then whatever P matrix comes out of that, the positive definite P matrix, I can use it in this formulation and compute a gain k. But remember, k is now a function of x actually, because every grid point it has to take a different value actually. So, we essentially come up with a nonlinear controller, but a linear looking structure essentially basically. Okay. And then there are implementation issues, because you are demanding an online solution of Riccati equation. How do you do that? So, first of all, if it is possible, then Riccati equation can always be solved by longhand algebra, especially if it is a 2-dimensional problem. Sometimes these 2D guidance problems and all that people have done it. So, they analyze the Riccati equation kind of extensively in the symbolic form itself and come up with some sort of a symbolic solution. That is the best thing if it is possible. Okay. Otherwise, the next best is probably use some sort of a symbolic software package to solve the Riccati equation symbolically. There are a variety of softwares available, something like Maple, Mathematica, MathCAD, things like that can be used. And then solve the Riccati equation. Otherwise, if it is that also is not there, then you have to solve the Riccati equation online with a very high speed computer, and that is no more a distant reality. I mean, it is actually a reality, because now people use even for aerospace applications, people use Power PC and things like that. But then for ground based applications where you can actually implement some sort of a fast processor and all with relative ease actually. So, that is not a very big deal, it can be solved online also. Okay. If that also is not possible for whatever reason, then we can always get some sort of offline solution and go for gain scheduling ideas actually. Okay. Then SDRE results, not only it is just intuitive and hence elegant also for implementation, but it is also backed up with some sort of nice results actually, nice analytical theoretical guarantees actually. So, one of that it tells that, okay, LQR solution is always guaranteed to be locally asymptotically stable. Okay. And for scalar problems, it is guaranteed to be optimal. That is what these theorems tell. And then why it is suboptimal, it is not necessarily optimal, is because of the fact that out of the necessary conditions, state equation is anyway satisfied. In addition to that, optimal control equation is also always satisfied. The one that is not satisfied is the co-state equation actually. But this co-state equation will also get satisfied asymptotically. As the control starts getting applied to the system, it will get it will start satisfying actually. Okay. Then it also, this framework gives some sort of extra degree of freedom, which tells us that, okay, even though this writing this SDC form is non-unique, okay, so people can write in a variety of ways, still you can come up with, okay, somebody comes with A1, somebody comes with A2, and both are two valid SDC parameterizations, remember that. Then somebody else can be little more smarter and tell, well, wait a second, I can actually formulate a A3, which is a convex combination of this A1 and A2 in that form, and then it gives me an additional adjustment tool or tuning tool alpha, which I can actually adjust it. If I am able to adjust it in a good way, then I will get a much better solution using A3 instead of either A1 or A2. And in fact, we have given some 2-dimensional example when we are discussing this SDRE lecture actually. So, you can do some sort of a offline optimization formulation and then come up with a proper value of alpha, so that this A3, which is derived out of that, some convex combination like that, is a valid SDC parameterization, which will give much better results compared to either A1 or A2 actually. So, that kind of things are also available. Okay. And then whether A3 is a valid parameterization or not, this is very easy to see. So, that is actually a valid parameterization, because once you plug in this formula it actually boils down to same f of x. So, obviously, this A3 is a valid parameterization as well. Okay. Now, there are certain limitations of this design also we saw. Then first thing is it can only be applied to a class of nonlinear problems. That means, the system dynamics has to be controlled affine especially, and the quadratic cost function has to be taken. So, that confines to the class of problems where this thing can be there. But remember, it is not a major restriction in the sense that many practical problems do naturally fall into that framework actually. Alright, then it has to suboptimality of the controller. So, it actually leads to kind of a suboptimal control, because all the necessary conditions of optimality get satisfied only towards end. That means, only asymptotically the co-state equation will get satisfied. So, that way it is suboptimal actually. Then we had non-uniqueness of parameterization was a major difficulty. That means, how do you write this f of x equal to a of x times x? That becomes a art, that becomes a lot of open questions there basically. And then we have this application, it is the entire design is applicable only for infinite time problems, okay, because Riccati equation has to be solved. It cannot be a dynamic equation, it has to be algebraic equation. Algebraic equation demands that the TF has to be infinity actually, okay. So, that is applicable only for infinite time problems basically. Then you also see that it actually demands the solution of Riccati equation online, which may not be feasible for high dimensional problems especially. So, if your system dynamics has something like 50 states, 100 states and all that, which is not I mean it's okay, some problems may arise that way, especially this structural control problems, or let us say vibration control problems like that, if you talk about that, or say in general this distributed parameter systems, infinite dimensional systems where large number of states are required actually that way. So, those kind of problems it may not be possible to solve this Riccati equation online actually, okay. Now, no analytical guarantee of global stability is available, okay. Even the local stability is there, global stability is never there actually, okay. So, that is what we discussed as up to SDRE, and then this is where I will stop this lecture, but the next lecture we will continue this review and then saw very quick glimpse of many other things that we have discussed as well. Alright, thanks a lot for this time.